I thought at least get through the initial things before the end.
We also have only 2 minutes until the start,
I have coffee. I have coffee. I have some coffee.
We're just getting set up in here.
No worries. Should we? I don't know if people can hear us. Should we keep muted?
We can kind of hear you. Might be better if you all have like thoughts or questions to type in the chat. You're being like broadcast to the whole room, just so you know.
Yeah, that sounds great.
Cool. All right. Got 1 minute?
Got 1 minute.
Give everyone a minute so we start actually on time.
Yeah. You start on time. What?
Wow. Yeah. It's the characteristic lull of. All right, it's 2 o'clock.
Okay, let's go.
All right, everybody. Thanks so much for coming to the Preparing for Future Observatories session. We're really excited to get your thoughts on how Code Astro potentially can like help you and fill gaps in your education for the future of astronomy. So just to give you a sense, remind you of the purpose of this session, we're treating this kind of like a focus group. So astronomy in general is changing a lot very quickly, and we're trying to get a sense of how Code Astro should grow and adapt, especially like thinking about the future of astronomy and coding in astronomy specifically. So the structure of this session is we're going to take the first 15 minutes or so to talk about some like near future like observatories and like data challenges that we anticipate. And then we're going to get y'all's thoughts about what gaps in your education you see and how Code Astro might like sort of plug in to fill some of these gaps. And then we're going to have a big group discussion. So we've structured this, each of the 3 of us have prepared some slides, and so we'll just sort of go back and forth and present. So I think that's up first.
Yeah. Okay, yeah, so one of the first missions we wanted to talk about was Gaia. So if you're not familiar with Gaia, this is an optical telescope that has produced an all-sky survey of star positions, motions, and parallaxes. This satellite has operated for a while. It operated from July 2014 to January 2025. And currently, there is a catalog release out there that you can access, a Gaia catalog DR3. It contains about half of the mission data incorporated inside of it. And it contains 1.8 billion sources. So 1.8 billion of these position, motion, and parallax measurements. And that can be accessed via the Gaia archive. Right? So why are we talking about this as a future mission? Well, that's because there are much larger data releases from Gaia that's coming. In fact, right on the horizon, we have Gaia DR4, which is scheduled to come out in December 2026. This new catalog release is going to use, I think, is it the full mission? Well, use about twice as much data as DR3. But one of the big differences is that instead of just reporting one position, one motion, and then one parallax for the sources, you're going to get the single epoch position measurements for each star. And there's something like 14 measurements of a star per year, right? So we're going to get a lot of brand new single epoch position measurements from Gaia. And then eventually, looking in the long term, there's a DR5 scheduled to be released sometime after 2030, right? So this is going to be a big new catalog release coming.
There's also lots of all-sky surveys coming online. Rubin Observatory is probably one of the big flagships that you've probably heard about. Just achieved first light recently, and the first science data and alert streams are coming down. This is a extremely large wide field camera, 3.2 gigapixel camera. A single image has billions of pixels. It's going to collect 800 of these images a night, about 10 terabytes of data a night. And the survey, over a decade will collect 2.1 petabytes, a number that I don't even know what that means. Amount of data was 2.1 million images. And we're getting to a point where these images and data are so big you can't store this data on a single laptop. We can't run processing code on the laptop anymore as a result. And how do we efficiently, how do we sift through this data, and how do we do it efficiently, for the science cases you want? And Rubin is not the only kind of all sky survey that's kind of starting. We have in the field, there's like a lot of astronomy that's kind of doing like rapid detection and follow up of various astronomical events. So we have a lot of facilities that are either online or coming online, like existing facilities like the ZTF and SWIFT, but also future all sky facilities like Argus, and also not just in the visible and X-rays, but also in the radio with something like the DSA. They're going to be surveying the whole sky, finding new and interesting phenomena. And usually, people want to catch these things as early as possible. You want to get you want to get a spectrum, or you want to get some other observation to understand what it is, if it's a thing that you're interested by. And there's all these follow-up observatories, like existing instruments like X-Shooter on the VLT, but also new generations of kind of spectroscopic follow-up instruments like LFAST. And when you're trying to do these things, as with all of these events happening, all these how do we quickly and reliably find interesting events, things that you want for your science, not just like whatever happened in the night sky? And how do we get to taking data and understanding these events as quickly as possible? How to reduce that, what's called latency? And then there's only a finite number of telescope resources out there. Each of these telescopes we build is a big investment for the community. How do we coordinate and most efficiently use all of these telescope resources to do rapid detection and follow-up of the most interesting sources, things that we don't expect? That's how discoveries often are made in astronomy.
Yeah, and building off this idea of upcoming surveys with lots of data, if we go to the space regime, we've got the Roman Space Telescope, right? So if you haven't heard of Roman, this is a very wide field near-infrared imager. It's going to be launched very soon, August 30, 2026. As I said, it's a near-infrared telescope. It's got a 2.4 meter diameter mirror, right? And the special thing about Roman is that in a single field, its field of view is 0.28 square degrees on the sky, right? That's 200 times larger than HST WIFC-3IR, right? So this thing's gonna launch. It's got a 5-year primary mission. This particular telescope, it's primarily a survey telescope. Most of the telescope time is gonna be dedicated to what are called these core community surveys. If you're interested in those, you can click on the link we have in this slide here. And there's going to be some time for PI-led observations as well, right? But we're going to have all the same challenges with Roman that we will kind of with Rubin and the telescopes Jason was talking about. We're going to have a huge volume of data coming from Roman. We're talking 1.4 terabytes per day. And the stat I saw was that over 5 years, Roman would produce 20 petabytes of data. Right? So this is huge, such a huge volume of data that this isn't going to be something for the vast majority of cases that we're going to be able to work on our own laptops and our own research machines. So we're going to have to work on the data in another paradigm, another way.
Yeah, so like right after Roman, we're going to have yet another space telescope working in the optical and infrared. The Lazuli Space Observatory has a wide field camera like Roman, but also will have a optical and infrared integral field spectrograph to take images and spectra, and also a extrasolar chronograph to try to do exoplanet imaging. We're kind of hitting kind of similar themes, but these observatories all have many themes, like trying to do like fast turnaround science, being able to quickly move your observatory to position to do the most interesting thing that is happening in the night sky, being able to take that data and quickly produce science products that we can use for interpretation to inform our next decisions. And also interesting for this telescope, how much of the telescope can be built with kind of off-the-shelf hardware components rather than very bespoke optics, like sometimes that happens with NASA missions. So this telescope was, despite all that, will have a large amounts of data and a large variety of data. And how do we best analyze and use that data quickly and maximize our scientific value?
So another really big sort of explosion in the scientific world right now is stable, high-precision Eshell spectrographs, which have been specifically used for extreme precision radial velocities. So the idea of this is to try to get repeated spectra of stars over various timescales, from very short timescales to very long, like even decades-long timescales, and eventually try to overcome stellar noise that adds uncertainty and correlated noise to these measurements in order to discover even ever smaller exoplanets. So some key technical challenges for this new suite of instruments is wavelength solution stability on both the hardware and the software side, making sure that you have like a constant ruler that you're measuring your wavelengths with respect to. And then also, as I mentioned, understanding stellar variability. This is a sort of interesting regime because we have very big data in the world of extreme precision radial velocities. We have lots of metadata, we have lots of telemetry, but we're currently not really using all of it. We're compressing like a spectrum plus maybe 100 calibration frames into a single radial velocity measurement, and then trying to understand stellar variability and look for planets with that single measurement. Another technical challenge is very complex pipelines. These instruments have a lot of like light bounces, and there are a lot of hardware components, and so writing a pipeline that actually produces a meaningful result and also can be maintained over time is really non-trivial. So here are just 3 examples of some extreme precision radial velocity spectrographs, but they're like on the order of like 20 of these nowadays, and new ones are still being built. Another general paradigm shift that we're witnessing that I think both Jason and Matt alluded to is data side computing. So in general, nowadays we have lots of data sets that are too big to download. So we're not going to be able to, you're not going to get the FITS file emailed to you or, on a hard drive, and then you can work on the data on your own computer. The data is not going to be able to be transferred to individual people. Moving into this regime, we're going to have to bring users to the data instead, put the data in one big place, and then have you do all of your computations in that environment. So we anticipate there will be plenty of educational gaps as astronomy moves into this new regime. Like running efficient code on high-performance computing systems is probably something that is going to be new to many people, and we anticipate is not going to be part of like most graduate astronomy curricula. Also just cloud computing in general and remote environment management. And I've got some logos for 2 commercially available data side computing platforms that exist nowadays. Many of these have already started to be adapted for various challenges in astronomy, but I'm sure we'll see many, many more of these as these observatories mature.
Yeah, and an example of one of these data side computing setups is what Roman is going to have. Roman is going to have this Roman Research Nexus, or RNN, which is a cloud-based platform to work on Roman data, exactly what Sarah was talking about. So the Nexus is going to provide a deployment of Jupyter Lab, a Jupyter Lab environment that runs on AWS, and you're going to need to use that in order to access Roman data and to run supported software. And exactly, the idea again, it's you want to bring the tools to the data rather than the other way around, bringing the data to your own laptops, to your own tools. And exactly, a challenge with this, actually we saw this, the cycle 1 call for the Roman telescopes for investigators. They didn't just have to say, oh, okay, I need this amount of money in order to hire students or whoever to work with the data. I also need this number of AWS credits in order to run my analysis on the Roman Research Nexus. So this is kind of one of these educational gaps. It was certainly something I wasn't familiar with, and so this is something we're all going to have to learn.
Yeah, on the ground, the same things are happening to Ruben. Ruben, like one of the things it's going to do is, looking for new things that are happening in the sky, things that are moving, that are not static. And a single one of these Ruben images will have maybe 10,000 quote unquote alerts, things that are different from their reference image. And many of these things could be like asteroids and things like that. That's what's marked in this example image. But sifting through all of these 10,000 per image, 10 million per night, how do you find, again, the interesting things for your science? How do you decide in a timely fashion what things to follow up? How do we make sure we don't miss interesting events, especially if we try to automate this? Like, oh, we're going to build machine learning tools, we're going to do this. How do we understand, how do we understand enough about these algorithms that we build that we know how they work, what are they getting, what are they missing, what are they specialized good at, what are they not so good at, and things like that.
Yeah, in general too, I think this is not going to surprise anybody that we're really sort of already in this age of AI. And a big sort of question/problem that we see is how do we stay grounded in physics when many AI models nowadays are hard or impossible to interpret? So we also think teaching things like, actually understanding large language models, looking at the underlying architectures and thinking about what transformers actually are, for example. And then also grounding ourselves in Bayesian statistics and modeling, so we understand how confident we are in the result that you get, for example, and also, connecting back to what your actual expectation for the output was. All right, so as you can tell, we have thoughts about what we think the sort of educational gaps are, but really the purpose of this session is that we want to hear from you. So we're going to give you 15 minutes in small groups to discuss these questions. Don't feel like you have to restrict yourself to these questions. This is really just we want to hear what you want to tell us about the future of Code Astro. So we want you to assign in your small groups at least one recorder and one reporter role. So the recorder will take notes in this joint Google Doc. So to avoid some amount of chaos in the Google Doc, I think it would probably be best for every group to make its own tab. So you can just click the additional tab here and then just label it with your group number or name or whatever. And then the reporter at the end will come up to the front here and just briefly summarize the discussion for the big group. So we're going to do 15 minutes in these small groups. Then we'll do 10 minutes of the report out where the reporters will come to the front. And then at the very end, we'll leave some time for a big group discussion inspired by what you all talk about in your small groups.
And feel free to merge into bigger groups if you want. So if you just a group of 2, you want to talk with maybe a group of 4 or 5, feel free to find a neighboring group and merge into a bigger meta group to talk about these things. And whatever you write down, we're interested to hear.
Yeah. All right, so we'll give you 15 minutes starting now.
Yes. Come back at 31.
Yeah. All right, y'all. Thanks so much for your time taken to put together your thoughts. So if we could have the reporters from each group come line up over here so we have some like semblance of order, that would be great. And then,
Everyone can talk for a maximum of 1 minute, so you don't have to say very much if you don't want to say a lot.
yeah, basically just want to hear a summary of what your group talked about.
Oh, nice, everyone brought their computers.
No, I know. I feel like it makes me feel I was like, oh, this is my burden.
That's okay. All right, ready? Yes. Cool. Am I just talking?
Yeah, go for it.
Yeah.
Okay, so we discussed, like regarding the first prompt, mostly just kind of reiterated what we talked about. And we also talked about how we might have to think about developing like more science and more kind of like methods that go along with like reducing this new data and like working with new data. And if like we're learning anything else, like what we might have to, I guess, incorporate to work with that. And also just not even necessarily the observatories, but just how to like code with AI responsibly, because that's kind of an upcoming thing. And then on gaps that exist, we talked a lot about how we didn't have a lot of like formal data science education in astronomy in undergrad, and like how we don't know about like MCMC or nested sampling or like the difference between the two, or like Bayesian statistics as a whole. And also like science and computing clusters and understanding how to use them and also how to use them responsibly. And so even though that wasn't necessarily like the theme of the workshop, we talked about how that could be something that like, would be really interesting to get out of something like this or like even this. And then how Astro could fill those gaps. We thought, we didn't know if this was like, I guess in the scope of Astro or not, but we thought it could be interesting to have optional like lectures or like courses or even just like material that's kind of, you know, teaching you how you could think about like writing an MCMC code or, you know, like working with a data pipeline or something. Because those are like really interesting, like code related things in astronomy that like a lot of us don't really have a lot of background in going into this. We also talked about thinking about more contemporary code like Julia, which I don't think we're talking about here. And also like if we're thinking about developing a package, like if it might be a good idea or not to like move forward with. And like what things to consider.
Awesome.
Thank you.
Yeah, first of all. No, that was great.
That was great.
Yeah, perfect. All right.
Okay, so for the first one, we kind of generally talked about the stuff we had already been mentioned, but one of the things we also talked about is how it's not as accessible to people who might not have as many resources to begin with, because we're kind of looking to find a solution to really large data sets. And then I guess another point to that is also, if you need to buy these tokens, you need to have more money to give out. So funding might be an issue. And then for gaps, one thing we talked about is like building and implementing custom pipelines, and then cloud computing skills. Also, we also talked about how we were never like really formally taught how to use like databases and archives like mass properly. I feel like I kind of just learned the few things I needed and I couldn't tell you how to do anything else on that platform. And then having a proposal writing class. And then for the third one, we said like using the databases could be like helpful to learn for Astro, which might be a little easier to fit in the chunk of time. We also mentioned how maybe doing like an online mini series for things that aren't necessarily like coding, but you can easily follow online, or possibly expanding the workshop to have maybe like either a week and a half long one, if that's feasible, or or like multiple times a year, and maybe you can attend a specific one that might be catered to a specific topic.
Yeah, awesome. Thank you.
Thank you.
You all can go. So
Okay.
yeah. I didn't want to like interrupt.
So for the first one, we talked about how like since there's going to be so much data, there needs to be so much also the processing and human review to scientifically correct and also understand what this data can look like or how this data can be utilized. Therefore, it's going to take so much time than what we are spending right now to detect the anomalies or like deviations that can be used in the researches, because now there will be a huge amount of data. And this is also going to cause a lot of missing data in terms of who is going to use it and how it's going to be used, because the identification and the filtering of this data will be harder compared to working with like what is going on right now. Therefore, like we come up with a solution which can be said as communication and collaboration can be like somehow a good contribution, because in that manner nobody can like not iterate, but replicate the processes that is going on. And then there was another concern which is saying that it's going to take a lot of more processing time to actually understand the data, because as Matt mentioned, now there's like clouding services and web services being included in the process of understanding and reviewing the data. So this is also causing another requirement, which is like a web service funding and those kind of things for the research. Those for the first question, and we didn't have time for the third, so I'm going to improvise with the like third and second combined. So there is now a requirement of learning about machine learning to classify and process the data. It's not like a requirement, but like it's a tool that can be mostly make things easier, like a lot compared to other ones. Therefore, like if you go a little bit deeper, we need to understand like the programming and the library applications better, because most of the astrophysics classes or courses are not deeply going into fundamentals. So people need to understand things like Git or Git workflow from like different resources. And also, if you want to understand these kind of things, there was somebody said that we need to have like a proper statistic course where we understand the basics and fundamentals to like data applications and then data reviewing. We talked about how we can actually also implement like a mathematical perspective, or how much we can go into that, and how, or if we can somehow implement real analysis into that. And something like a pure mathematics and something in between data can be really helpful to like have a basic standard that we said. And yeah, I guess that was pretty much it from our group as well.
Thank you.
Yes, so our group talked about how the fact that the new level of data flow coming in requires techniques of like machine learning to actually fully understand and interpret and otherwise do research on this data. But the issue is that this differs from traditional computation methods, because you can't really fully understand what these really deep level research neural networks do. So how do you ensure that things are physically accurate and your results are physically appropriate in this sort of age? And actually, people don't really know. It's a question of open research right now. And it sort of goes against like our teaching, our foundations of like, you can model and predict quite well, when in reality, with all of this data coming in, you will have some fundamental uncertainty in your results. And we also talked about how the fact that this means that there's a whole new skill set that people actually have to learn now, is using these supercomputers, using these neural networks, and how to actually integrate that. And it's something completely missing from our education. I mean, I'm not sure about other places, but we were taught enough to code, right? Scientific computing, they called it. But we just aren't taught how to manage these environments, how to actually do research level code of this sort of stuff. We aren't taught how to engage with other machines, how to make sure our results actually look good as well in terms of like usable by other people. So a massive thing now is a lot of research level projects are huge and the bigger tasks. And so it's not okay to just design simple scripts. And yet any sort of project design is completely missing from education. So basic software engineering principles just aren't around. And that's actually a thing also in established researchers. So sometimes research level code is hard to read, poorly designed, and otherwise hard to use. And that's a big issue when we rely on each other so much, especially when they come from our fundamental surveys. So it just doesn't prepare enough coding knowledge or background for an average physics research environment. And we also thought as well that this sort of reliance on big data, so talking about like the AWS and things, it adds an extra barrier to research because now you need credits. There was a time initially where you could download archives of data from all these public research points. That's kind of the point of research, right? Being sort of quite open and accessible, and you can replicate it. And yet now you need advanced hardware, even though you need like supercomputers itself, access to that to reproduce or even work in that same field. You need credits otherwise to engage with that data as well. And we didn't do too much of the third question, but it teaches some of the most important parts again of software engineering and how to actually design code and how to actually have it be a full complete project. So it's a pretty good workshop as well. And that's our like summary.
All right, thank you very much.
Yeah, so adding up to what other people have already said, I think that the main thing we discussed in terms of challenges is just big data and how much the amount of data that we are used to working is how much the scale of the quantity of data that we are used to working as an astronomers and scientists is going to change very rapidly from now on. And that's not the only thing that it's changing. Like those large language models are becoming exponentially more powerful, and that's also going to change the way that we do science. There was this Harvard professor that published a paper in 2 weeks with Claude that should have taken him 2 years to do with a grad student. So there is understanding our role in the age of AI and how do we use those tools and how do we leverage them without letting them leverage us. I think that's going to be a big challenge. On that line, working with supercomputers, like learning, like you guys said, we're not going to be able to run our analysis on our own computers anymore. So how do we work with supercomputers, computer clusters? How do we learn the different network software terminology and stuff that we need? So in terms of like gaps that exist in our education, the first one is understanding how deep learning models work and how we can leverage them. There might be a huge shift in terms of like the majority of the data science models that we're going to use will have something to do with deep learning to be able to account for the big amount of data. So we were not trained on them. So understanding how they work and how we can use them. And also many students don't know how to use supercomputers and computer clusters and stuff like that. So that would be like super helpful. And in terms of things to do in the workshop, again, just, more education in LLM models and AI in general, in a sense of like as a tool for data science. So like not teaching us how to use Claude, but like teaching us how Claude works so that we can leverage the foundations behind to make our own models and analyze the data. And also learning how to navigate like different types of supercomputer cluster software would also be useful. Yeah.
Awesome. Thanks.
Thank you very much.
It seems a lot of the more technical things have already been talked about up here. So I got for the first one, a lot of our group talked about junior scientist challenges specifically. Like if you're trying to learn as a junior scientist and you're trying and making mistakes as is part of the process, but you have a limited number of compute hours or the tokens, how do you manage that? And how do you have upper management or whoever's deciding to like distribute these tokens to like justify giving it out to junior scientists so they can onboard versus someone who already knows what they're doing and just can keep running the code, and being efficient with that as well, and how to like integrate workflows with high performance computing, like SSH into Git, large Git collaborations more than just like a small group, but also like integrating like, oh, my data's in this computer, but I have computing hours on this cluster. How do I use Globus like transfer over here, and how can I do that efficiently without messing up everything? Or getting used to batch coding. And same with education. Like a lot of us haven't been trained specifically to be data scientists for astronomy or have switched career paths or switched majors in some way. So how does that gap in education get covered by this? That's already another barrier to entry. In terms of Code Astro, we were talking about like you don't want to cram too much stuff into Code Astro already. So like we were thinking like this is pretty good, except for like this is like a pretty good pace for everything to learn it, and it's necessary. So we're like, oh, maybe there's a Code Astro too. But it's just all SSH and supercomputing with a similar structure to like actually practice it versus just going to a 1 hour lecture where someone tells you how to SSH and then you never know how to actually practice using it.
Awesome. Thank you very much.
Yeah, so for us, the main challenges that we talked about, this is like more about like, I guess, funding of like where these future observatories are like coming from. Cause like, we were kind of talking about how like, it'll come, at least government funding will come from taxpayer dollars. And, it's kind of a little bit difficult to like sell that to like, somebody who might be struggling like financially to like say like, oh, hey, like, here's some of your money that's going to go to like this like pursuit of knowledge stuff while you're kind of trying to pursue like, paying like, your bills and whatnot. And so, yeah, we were just like talking a little bit about like the like political challenges that come with these future observatories. And then, yeah, also like all the AI and the cost of all of that. Yeah, kind of connecting to like the discriminatory lecture earlier. For the gaps, we talked actually a little bit about like how to write like a research paper, because like, and like how to read one as well, because like I don't think like many of us were like taught that. Like we were taught how to like read and write, but that was like from like English class and stuff. So, you know, we know how to read like a novel and how to like write an essay about said novel. But then when you try and read like an actual paper, it's like formatted very differently. And then like writing it is also formatted quite differently. So yeah, that's a bit of a gap. And then also as like a group of undergrads, we weren't really sure, like, you know, there's some unknown unknowns, at least for us, having not done too many research projects. So we don't really know, like, you know, what we're gonna like stumble upon, like, you know, and get tripped up on later on. So yeah, like maybe some stuff about like how the research process is and whatnot. And then how it could be, how Code Astro could be better. We weren't really sure. I mean, like, just, you know, obviously like more time, more lessons and stuff, like a little bit tough to ask for, but you know, just more time.
Thank you.
Thanks.
Yep, so a lot of what we talked about has kind of been mentioned, but I'm going to try and highlight the main things, which is we talked about how there's going to be lots of infrastructure for storing like the big data that is going to be coming from like Roman and Rubin, but we aren't necessarily going to have the skills ready to like have speed and efficiency of processing the data. And another limitation that's going to come up is if you want to use multiple data sets together and do comparisons, then if those data live in like different platforms, then how do you merge those when you can't house them locally? And in terms of gaps that exist in our education, one of the things that came up was data management, where we are kind of taught to like use existing catalogs, but we're not really taught explicitly in our classes on how to make catalogs of our own or how to manage data in like a organized and consistent way. And with more and more, with like the magnitude of data that we have in different specialized fields increasing, we are kind of losing multi-wavelength breadth, and we're kind of becoming more specialized in working in a limited wavelength regime. So with like Roman, you have so much data with Roman, you might just focus on staying in optical infrared and not really focus on not do multi-wavelength astronomy, which is something that is becoming more and more of a gap in education. And something else that came up was not a data access and how to use the amount of, how to essentially, like, if things are going to be limited by credits, then that is going to impact learning if someone else can do that task more efficiently. And for the last question, we talked a little bit about having maybe aspects of data management be taught in Code Astro, as well as cloud computing and high performance computing in general. And we also talked about how statistics is something that we feel like we have as a shared gap in knowledge, and perhaps that some elements of that could come up in future workshops with like common methods, concepts, and how to apply certain statistical techniques in different situations. Yeah.
Very awesome.
So yeah, a lot of people kind of covered the topics that we discussed earlier, so I guess I'll discuss in terms of themes. So with the first question, a major theme was an issue of accessibility. Mentioned before the HPCs, you either have an issue of your university having HPC and having to allocate resources, or your university doesn't have HPC and you have to get tokens, and that kind of that creates a whole other issue of gaps in being able to access it and use it. And then there's also, even once you do have access to these things, it's understanding and utilizing these abilities is also a whole other area of skill that is a gap for some. We mentioned how it often feels self-taught, and so like workshops like these are very helpful. We also mentioned, like, if you're an undergraduate, you know, especially since these are very early career scientists, these are people who have felt the brunt of these future issues. From my own perspective, at least as an undergraduate, access to these workshops are not as easy. I mean, I'm here mostly out of just knowing the right people, but when you're an undergraduate, you don't know a lot of people at all. So that was kind of another issue we talked about, and we mentioned kind of like online aspects like the live streams and general online resources for these future problems to be accessible to everyone could help both undergraduates, but also if you're like a professor in a later stage who's not so used to these new softwares coming up, people mentioned in our group how people have good ideas, but they're not able to really use it properly nowadays because they don't know the way to use the tools that exist currently. And so for the second question, the best way it was described in my group is that as you go on, as a scientist, you have to get so many hats. You have to be a statistician, you have to be a data scientist, you have to also know astronomy, you now need to understand supercomputers. And so there's a lot of skills that come with it that's kind of hard to really wrap your head around and know what you even need. As an undergraduate, you're limited on what you know, you're limited on what you think you need to know. And so you focus on very specific things, and then it comes to grad school, and now you need to understand statistics, parallelism on PCs, coding in anything that's not Python, like just publishing nice figures and presentations and conferences. These are skills you didn't think in undergrad, you probably just focused on like passing your classes, but it creates gaps that education should probably address in some form. And then our group didn't get to number 3. Thankfully, all other groups had a lot of good suggestions that I assumed that my group would also agree with. But yeah, I guess off the top of my head, online resources would help with the quiz we're talking about with undergraduate people not having opportunities to learn about these future problems. And I think you guys are doing a good job at that. So thank you.
Thank you.
Thanks.
So we also talked a lot about what people have covered, and we specifically focused more on like 2 and 3, but like for 1, the big theme was just a lot of data and not a lot of time, resources, or people to really understand and go through that, and also just limit of accessibility. And more about the gaps, one thing that we were talking about is that some fields are just kind of outdated on like where they stand with the current methods that they use, and that might be a really big issue once you have more of these future observatories and your methods aren't updated, so you might not even know how to handle that and be equipped for that. And also in general, a lot of people have mentioned this already, a lot of just undergrad programs, they're very different in the education, and some of them, at least I know for mine, did not require any formal stats training and like a very basic computer science course. But then as you get further in the career, you need to know all the stats, a lot more computer science, and with having a lot of data, knowing how to optimize your code and have better run times and all that is a lot more important. So having your really bad coding habits that you might develop from not really knowing much basics of CS is a big problem. And sort of how to fill that, the methods with just like fields being kind of outdated, I think we talked about a little bit, maybe some interdisciplinary collaboration and sort of being a little bit more like, oh, what are other fields doing? Like computer science, like what's up to date there? And I think having like some way to like keep up to date with that. And I think Code Astro is a really good, second point, got ahead. Code Astro has been pretty good at sort of being geared towards especially like the graduate student level of like teaching and getting those basics down. But I feel like more outreach, especially if there's like maybe a Code Astro specifically for undergrads and stuff, and sort of bridge that gap there, and maybe even like very like early career grad students, or have like a specific version for people who are later in the field, because having like a specific demographic, people might feel intimidated or just feel like, oh, if I'm senior in the field, why would I go to something that seems that's more geared towards people who are like my juniors? And so we kind of talked about that too.
Nice.
Yeah, great. Yeah, thank you very much.
I'll keep it really quick. I just wanted to slide on a few more points that, in addition to all the fantastic ones you guys brought up, when it came to new challenges with data flows and observatories with all this data, one of the things that I think about a lot is how do we report null detections? If you have a program where you're looking for the flares in some subset of the data, how do you say, I also looked at these stars and didn't find any flares? Because that's also useful information, but oftentimes people just report the things they do detect. And for smaller survey missions like TESS, I can run the whole TESS archive. I'm not gonna be able to do that for Roman or LSST, so I have to be able to communicate, I looked at this portion of the data and I didn't find anything. For the second one, I think you guys all covered stuff really, really well. For the third one, for what could Code Astro do, one thing that I was thinking about a lot when we were talking about the big data and about working on SSHing into things and working with remote resources is it might be really useful to cover an introduction to how memory works in Python and how that relates to efficiency of computing, because there's some subtleties in how data is stored. That means that using the append function for a list is way more efficient than saying list 1 plus list 2. But if you just look at that on the surface, there's no reason you would just know that from looking at it. So maybe there's some opportunity for like a low-level dive into what actually is efficient and what are some best practices for when you're trying to write code that is efficient, both in memory and in compute power. So those are 2 things I wanted to add.
Awesome. Thanks, Ray.
What about the folks online? Is there a reporter from the online group? If so, feel free to unmute and say some stuff. If not, that's okay too.
I know that we talked really briefly, but I actually think everyone did a really good job with kind of summarizing it from all of the in-person groups. But we talked a lot about, challenges being that we're all very used to this entire workshop being kind of predicated around setting up your own virtual environment and having, everything on your own PC, and that's going to change drastically. And gaps in our education are just everything that everyone has said. You have to be a statistician, a data scientist, all of the above. And again, yeah, I think we could probably do like 3 or 4 Code Astro workshops if we had the time and the funds. But yeah, there's always going to be more to cover. So
Awesome. Thanks, Lauren.
Yeah.
Okay, this was more than the 10 minutes of report out, but this is great. The main point of this was to hear from you all, and we really appreciate your thoughts and your feedback. This notes document will stay available, so if you think of anything else, or if you want to add something in response to what you heard other participants say, please feel free to edit your replies. We're definitely gonna look at them, so it's not just gonna go into the void. We're also gonna send out an end of workshop survey tomorrow that'll ask you for more general feedback about how this Code Astro went and how we can improve the current format of Code Astro, so you get other opportunities to give us feedback. Yeah, okay, I think that's it.
I think so.
Want to say anything else, either of you?
No, I think it's great. I liked all these discussions about
Yeah.
Code Astro 2 and Code Astro 3 and Code Astro 4. We've certainly floated around the idea, but as you can see, it's also not easy to run a Code Astro. So, but thanks
Yeah.
for all the great ideas. I think we're going to try to take your ideas and really digest them and think about how we want to move in the future. Because it's great running this workshop all the time, but I think there's also other things we want to address in addition to this workshop.
Yeah, absolutely. But yeah, thank you all again so much for your time. I'm really pleased to see so many of you from the main workshop in this optional session too. It means a lot to us.
Yeah, thanks for all your time.
Yeah.
All right.
Okay, thanks, y'all.
Yeah, thanks.
All right. All right, thanks online people. We're gonna head out.